In this video, we'll introduce the idea of maximum likelihood. So we've talked about estimators and mean squared error as measuring how well an estimator works. But how do you find an estimator in the first place? So let's start off with an example. Maximum likelihood is a way to find estimators, a principled way, a principle for it. So here's an example. Suppose that x is distributed as binomial 20 and p, where p is unknown. Suppose we observe x equals 7. So we perform the experiment and we get some result. That's x equals 7. Then we can write down the probability mass function as follows. And it just looks like this. This is applying the binomial probability mass function. The key concept is to treat this as a function of p. That's called the likelihood function. Because p is unknown, we could try different values of p. We could try p equals 0.5. And then we had f of 7. P equals 0.5 is going to be equal to 0.074. Maybe we try p equals 0.6. Then we'll get f of 7, 0.6, plugging 0.6 in for p in this equation here is what we're doing. This is equal to 0.015. So note that this is smaller than the one above it, okay? So that means that it's probably less likely that the true p is equal to 0.6 compared to 0.5. Then if we take f of 7 over 20, this probability, joint probability, becomes 0.18, okay, which is a little larger, suggesting that estimating p with 7 over 20 is better than the other two, because it makes the likelihood of the data that we've seen most likely. So this is the likelihood function. So let's maximize this likelihood function. Maximizing. F of 7p. This is the same as maximizing the log of f of 7p. So taking the logarithm and maximizing it. And the reason that is the case is because a logarithm is a strictly increasing function on the interval from 0 to infinity. So we can take the log and maximize that, and that becomes easier because the products become sums with the log. So this logarithm is log 20 factorial. Well, so here we plug in the expression, and then now we apply logarithm rules, which says that this is equal to we want to maximize it, so we can differentiate with respect to p. That gives us 7 over p minus 13 times 1 over p. 1 over 1 minus p, rather. So we differentiate, and then we set this equal to 0. So this is the idea of the mathematical optimization. We can now solve it. So we like, the MLE is the maximum likelihood estimate or estimator, and the reasons we like it are as follows. As we increase the sample size, so as we observe more and more data, we get better and better maximum likelihood estimates. So one nice property is that the bias goes to 0 usually. Important caveat, usually goes to 0. The other property is that the variance gets as low as it can be. So we want our estimators to have low bias and low variance. That means it's a good estimator. It will have low mean squared error. Again, usually this happens.